Okay, so your first one should be, remember everything is extended, so that's going to be 2 diagonally, 2 diagonally, extend that up. So let's go stage 2. Space in there. Okay, so there are your 6 fish. We'll say 1, 2, 3, 4, 5, 6. And now we're going to look at some patterns from those shapes, those diagrams that we've just drawn. So it says there's a relation between the growth stage and the number of dots making the perimeter of the fish. Use your diagrams to complete the first 6 columns of the table of values below. So the growth stage 1, the number of dots that make the perimeter, so you count them up. So 1, 2, 3, 4, 5, 6. Growth stage 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So make sure you don't double up, right? So 6, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 6, 13, 20. You can keep counting them, but you might see a pattern, right? Each time your number of dots is increasing by 7. Okay, so the next one would be 27, then 33, then 39. Okay, and it says use your patterning skills to complete the last 4. Well, we've already used it for some of those because we did see the pattern. So another 7 would be 46, 53, 60, and 67. I think I did. Nope, I did that wrong. We'll do the right pattern. Got to add 7. So that's 34, 41, 48, 55, 62, 69. There you go. Okay. This relation can also be described with a set of ordered pairs. Write the set of ordered pairs that describes it. So, growth stage 1, number of dots 6. Growth stage 2, number of dots 13. So we have to know the growth stage in order to know how many dots we're looking for. Okay. So recall that a function, is a relation where no 2 ordered pairs have the same x coordinate. That's not the definition, but that's how you can tell in the set of ordered pairs is if you have the same coordinate, x coordinate, and 2 different y's, then it's not going to be a function because that means for that value of x, there's 2 y values. So in this case, that's what we're looking for. But here there aren't any repeats. We don't have 2 growth stages with different sized fish. So yes, it's a function. Okay, so turn over the page. It says, recall that the domain of the relation is the set of all possible values of, okay, the domain is what you start out with. So that's the independent variable. You've got to know those values before you can find the dependent variable, like the y value. So write the domain of this relation. So in this particular case, I mean, this could go on forever. So for that table of values in that set of ordered pairs, it would be 1 through 10, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay? But in reality, we could keep drawing those fish forever. So in that sense, it could be, we're going to call these growth stages. We're actually going to use n. It's often used. So n would be an element of, well, what are those numbers if we keep on going forever? Those are natural numbers, which for IB notation is z with a plus. Okay? Means all the positive integers, which are 1, 2, 3, 4, 5, which are natural numbers. Okay? Range of a relation is the set of all possible values of the dependent variable. Dependent variable. Range then, well, we started out with 6, then added 7, that's 13, 20, 27, 34, 41, 48, 55, 62, and 69. In terms of writing that in any different way to go on forever, you could just put dot, 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 or you could write an actual equation that it represents, which we're actually going to find down here. Okay? So we'll just leave it for that particular chart of values that we did on the previous day. Okay, so note that the domain of this relation is a subset of the natural numbers, right? So 1 through 10 is part of the natural numbers. A function with a domain that is a subset of the natural numbers is called a sequence. Since we know that the domain of a sequence will always start at 1, 2, 3, etc., we concentrate more on the range of the sequence. The values of the range of a sequence are called the terms of a sequence. So the first 6 terms of this sequence that we're building from the diagrams of the fish are those values there. First 6 terms, 6, 13, 20, 27, 34, 41. Okay, so that's really the sequence that we're looking at. And the 1, 2, 3, 4, that tells you which growth stage or which term we're looking at here. We didn't know that this was for fish, for example. So the first term of this sequence here is 6. Notice the notation that's used, a T with a little 1. It's a subscript. So when you're doing this, which you will have to do, I don't want to see that. Okay? That looks like T times 1. It's got to be a subscript. Okay? In the lower corner, just opposite of an exponent. Okay? 6th term of the sequence. So that's 1, 2, 3, 4, 5, 6. That's 41. And notice the notation. T with a little 6. Not a big 6. Okay. How do we denote the 10th term? That would be T with a little 10. Okay. And then what is the 10th term? Well, we did it in our chart actually. So if we looked back to the 10th growth stage, it was 69. Okay, and then the relation between the growth stage and the number of dots can also be described with words. Complete the following sentence to describe how to determine the number of dots for a particular growth stage. Basically, what's the formula in words? So how can, if I said, what's the number of dots for the 20th fish, growth stage 20, what could you do? Well, we do know that each consecutive one is 7 more than the last, but we want to be able to, knowing our number of dots, do something to this, multiply, divide, add, subtract, whatever, in order to get that number, okay? So sometimes you might want to think about back to math 10, when you talked about linear functions, linear relations even. Okay, you would look at, okay, each of these are increasing by 1 each time. Each of these are increasing by 7 each time. So that means our rate of change is 7. So determine the number of dots. We multiply. So remember how you did an equation of a line? So you would then, if this was x and y, you would say y equals 7x, and then you would figure out the y-intercept. Basically, if it was 0, what would you get? In this case, you would get minus 1. So if you have your growth stage and you multiply it by 7, this is always 1 less than that. Okay, so multiply by 7 and subtract 1. Okay, so if you're not sure how to come up with that formula, we'll learn. This is an arithmetic sequence, and we're going to talk about that tomorrow. There's a formula that you can use. But until then, do a little chart back to math 10. All right, so use your results to determine the number of dots for growth stage 20. So that would be 20 times 7 minus 1. So what's that? 140 minus 1 is 139. So how many in growth stage n? That's your general formula. Okay, so number of dots equals 20n minus 1. That's your formula. 7n, not 20n. Got them mixed around, sorry. Look it up here. 7n minus 1. Okay, so the general term of the sequence is denoted by Tn and is called the nth term. Write an expression for the nth term. So basically now, instead of number of dots, I'm just using T subscript n. It's almost like function notation, right? We know that we're using n as our independent variable. We might go T bracket n. But if we're talking about these being sequences, then we use the subscript. That's kind of a hint. This is some type of sequence. Okay, so this n is the term number, and this whole value is this is the value of the term, right? Sometimes students get a little bit mixed up about that. N is the term number, and T is the value of the term. Okay? So verify the expression for Tn with the 5th term of the sequence. To do this, substitute 5, n equals 5 into the expression, and show that it's 34. So we know that it's 34, so we're verifying here. So this is going to be Tn, and this is 7n minus 1. So I like to verify in a chart like that, a T-chart, just to keep them separate. Okay, now working backwards, now we know the number of dots, and we have to figure out which term it is. So now this is Tn, and we need to figure out what n is. So 559 has to equal 7n minus 1. And we solve that linear equation. Add 1, divide by 7. Your n should always be a natural number. You can't have a fraction for n. We're dealing with this representing a sequence. N is a term number, so you can't have half a term, a quarter of a term, a small of a term. 7 is 56, so that's 8. Okay. So it's growth stage 8. Just going to expand this out a little bit. It's squishy. Okay, so a sequence can be thought of as an ordered list of objects. There's some examples of some other sequences. We always call the first sequence, the first term T1. Well, I shouldn't say always. Alberta curriculum does. And so when you get to the diploma exam, if there's something about a sequence, they'll use T's for terms. That makes sense, right? IB sometimes uses A for your first term, and then T's for any other terms. Because A is the first letter of the alphabet, so A is sometimes used as the first term, and your textbook might do that. Okay? And then they sometimes use U's with a subscript for the terms. I don't know why. These are different in different places. But in any case, most of our work will just be using T's. But in your textbook, or the textbook questions that we assign for some of these, if they've used A, that's your first term. Okay? So here you might want to put a note here. Sometimes. Okay, the nth term is denoted by Tn and is called the general term, where n is the term number. So, in question 18, it says a sequence can have a fixed number of terms, finite. Finite means it stops, it doesn't go on forever, and infinite means it goes on forever. Classify each of the above as finite or infinite. So the hint is, if there's 3 dots afterwards, then it's going to keep on going. Okay, the pattern will continue. So these are infinite. And this is finite. It's stopping at 23. It's still a sequence, but it's just going to stop there. Okay. All right, so we came up with an equation for the general term for the growth stages of the fish. We're going to do a whole lot more of that, but we also want to think about what's called the recursive definition. So if you've taken any computer science, you've done some work with recursion, right, to keep a number going back in to get the next and the next and the next. And that's basically what the recursive definition is for a sequence. You need to know the last term to get the next. Okay, so it's very difficult in a recursive definition to say, what's the 100th term? Because in recursive definition, you have to know the 99. To get the 99th, you have to know the 98th. So it's not something you use a whole lot of times, but it is something that you use in computer programming a lot, just that general idea. So you need to understand what it is. So the first 6 terms of the sequence are 6, 13, 20, 27, etc. Write a rule that compares, that should be the number of dots in a growth stage to the number of dots in the previous. Well, what happened, that's how we got all these. We keep adding 7, right? So each successive term, I'll put, is 7 more than the previous term. Using some of the notation then, it says the number of dots in growth stage 2, so T2, is 7 more than, there's the plus 7, the number of dots in T1. So you're just filling in that subscript. Then B, the number of dots in growth stage 3, is 7 more than the number of dots in growth stage. Well, if it's just 7 more, it's just the previous growth stage. So that would have to be 2 there. So growth stage 10, we have 7 more dots than growth stage 9. And then in terms of N, in growth stage N, that's 7 more than the previous growth stage, which would be N minus 1. So your subscript is N minus 1. And we always use lowercase n, don't use a capital N. Okay, the recursive definition for a sequence relates a term to the previous term. There are 2 parts to a recursive definition. The first is to state the value of the first term. If you don't know what the first term is, you can never get any other terms. Right? You don't know where to start. Second part consists of the rule. Okay? So for the fish sequence, we write our first term, and then our nth term is the previous term plus 7. Okay? Notice how all of those were plus 7. We actually found this already there. Okay? But just remember, so sometimes we all focus on the sort of the part with the variables, but if you don't know what terms that starts with, then you'll get the wrong terms. Let's say you didn't have that. Well, someone might say, oh, term 1 is 1. Well, then we get 1, 8, 15, 22, and that's not the growth stages of fish. So you have to have both parts there. And sometimes you'll see n is an element of a set of natural numbers. Kind of assumed, but you might see that in the question. Okay. Next one is not recursive because there's no t's over here. So we don't need to know what the previous term is to get a term value. It says determine the first 4 terms. So we're going to find T1, T2, T3, T4. Okay. So 1 squared is 1 minus 3, well, you can substitute it in. So 1 squared minus 3 times 1. So it's basically just substituting and simplifying. This one, 4 minus 6 is negative 2. Nine minus 9 is 0. 16 minus 12 is 4. Okay, so you wouldn't be able to come come up with just adding it by the same thing or multiplying in this case. It's hard to get a recursive definition. The next one is a recursive definition. So you're given the first term at 6, and then notice that you take the previous term, multiply it by 3, and then add 2. And here it says n is greater than or equal to 2. So remember, because here, really, if it was 1, then this would be 0. So really, I should maybe have been more specific here. So this would be n greater than or equal to 2. The natural numbers. Okay. So T1 is 6. T2 will be 3 times 6 plus 2. T3 will be 3 times that previous answer plus 2. So you can see I can't figure it out until I go through each step. Okay, so that's 18 plus 2 is 20. Now I have to put 20 in here. That's 60 plus 2 is 62. Now I put that in there. What's that? 186 plus 2 is 188. Okay, and then types of sequences. So classifying them. We're going to concentrate in this unit on arithmetic and geometric sequences. But there's millions of types of sequences, as long as you can find that pattern, right? So for each sequence, describe a rule that will generate a term from the previous term, and then write the next 2 terms. So what's the rule? Compare. So thinking about recursive definitions, so 24 to 29 to 34 to 39. Well, if you take a look, they're all 5 apart, right? So to get each consecutive term, we add 5. So then this would be 44, and that would be 49. Then 18 to 20.5 to 23 to 25.5. You might want to subtract successive terms, like 20.5 minus 18 is 2.5. Give me a sec. Okay, 23 minus 20.5 is 2.5, etc. So you're adding 2.5 each time. So that's going to be 28 and then 30.5. Next one, they're getting smaller. 12 minus 5 is 7, 5 minus 7 is negative 2. So here we're subtracting 7, which is the same as adding negative 7. Okay, so just be aware of that. So next would be negative 16, negative 23. Okay, then D, 5, 10, 20, 40. Well, those aren't adding the same amount each time. You're actually multiplying. It's like you're multiplying by 2 each time. So that would be 80, 160. Next one, positive, negative, positive, negative. So we're multiplying by a negative. We can't do that with adding. And then 7 times 3 is 21, times 3 is 63, etc. So multiply by negative 3. So what is, I don't know, 189. So that's going to be positive 567. Negative 1,701. Okay, next one, you are, what are you doing? You can give me what we're doing in the next one. Adding, subtracting, multiplying, dividing by something. Get each consecutive term. Hand up. Dividing by 2. Now, dividing by 2 is the same as, just to be aware, multiplying by 1/2. Okay. And so, if we divide this by 2, or multiply by half, we get 21 over 4, and then 21 over 8. Sometimes it's easier to figure out if we consider it to be multiplying. Right? But we don't like that much. Next one is a special sequence. Anyone know the name of it? Fibonacci sequence, yeah. So Fibonacci sequence says that you add the 2 previous terms together. So here that was going to be 34 and 55. Okay, so this kind of leads into what we're going to do over the next week or so. This means sequences where the same number, positive or negative, is added to each term to create the next are called arithmetic sequences. So a lot of students will say arithmetic. We're saying it as an adjective, so it describes the sequence, so we say it as arithmetic sequence. State which of the sequences are arithmetic. So if we're adding or subtracting, because really subtracting is adding a negative. So that's going to be A, B, and C. A, B, and C. Note for arithmetic sequences, the difference between consecutive terms is common. You keep adding the same thing. And that's why we call it a common difference. Because we take the second term and subtract the first. So that's a difference. That's how we get it. State the common difference for the arithmetic sequences in 25. So here, D, I'm just going to go back up and put them up here. D is 5. D is 2.5. D is negative 7. Okay? It's always the difference between them, so I gotta fix that. So it's always the number that you keep adding to get the next. So we would never say D is 7, even though we keep subtracting. So it's always going to be what number do you add. So we have to add a negative in this. Okay. So these are up here. Then sequences where each term is multiplied by the same number to create the next are called geometric sequences. State which of them are geometric. Maybe I'll change my color here. Okay, so where are we multiplying? So that's going to be D, E, and F. And for these ones, what number you multiply by, guys, is common each time, and it's called a common ratio. So the common ratio for these ones, so this, we use an R equals 2, R equals -3, and then you have to use this one, R equals 1/2. You can't say R equals 2, because then our sequence would keep getting bigger, and it's not, it's getting smaller. Okay. The last one is not arithmetic or geometric, it's the Fibonacci sequence, so we don't have a special ratio or difference. We would use a recursive definition. Okay, so in the arithmetic sequence, each successive term is formed by adding a constant term to the previous. The constant is called the common difference. And that's how you can find it. That common difference is going to be the same, whether you test between the second term and the first, the 10th term and the 9th term, 100th term and 99th term, right? Always the difference of consecutive terms. Geometric sequence, each successive term is formed by multiplying the previous term by a common value. And this is called the common ratio. Okay, and how do you get it? Second term divided by the first, 100th term divided by the 99th, just consecutive terms. So, as I said, some are not arithmetic nor geometric. That one that we just looked at was a Fibonacci sequence and is a large number of applications in nature. Okay, so that was, what was that, G? Yeah. Okay, and I think that's the last one. Yep, so now you can do some practice.